Okay. So we're investigating these homomorphisms. And where we left it was last time. We were in proposition 11.4. And the last part, part 4 of this, is where we're going to pick it up. So if phi was a homomorphism from G1 to G2, given any subgroup, he's calling it H2, G2, the inverse image of it, remember phi itself is not necessarily bijective, so there won't necessarily be an inverse function. Phi inverse, but we can nevertheless use the same notation and say phi inverse of a subset of G2, which is by definition is all the G's in G1 that ended up inside H2. This is a subgroup, G1, include that, and H2 normal in G2 implies the pullback of it, or the inverse image of it, is normal in G2? G1. G1. Yeah? Because that's where it lives. Yeah. That's where the inverse image lives. Yeah. So, okay, we proved that last time. So where we pick it up now is, or any questions on that? So we're going to introduce some terminology. We can say the kernel of a homomorphism. Now we're familiar with that, aren't we?
There was two sides to that coin, wasn't there? There was the kernel and
The
image transfer.
Yeah. So you talked about those for linear transformations from one vector space to another.
Kernel map to 0.
Yeah, the kernel map to 0. So what's the definition of it here?
The identity.
The identity, yeah. The 0 in the vector space is
Yes!
the identity. That's the identity in the vector space, the null space.
The null space.
It's also known as the null space.
Which sounds a million times cooler, so why do we call it the kernel? Because it just reminds us of KSE.
The term null space isn't used,
KSE of the homomorphism.
isn't used so much in group theory, I think. I think kernel is more common. But yeah, so you know the definition of this already. It's okay, so it's phi from G to, well, let's stick with it, G1 to G2. Kernel of phi is every G from G1 that gets sent to the identity. Now, what do I mean by E here? I mean the identity in G2. You can tell that from the context because I'm talking about it as an aggregate of phi. It's a value of phi. So this E must be the E in G2. You could put a little subscript on it. E2, identity from E2. Now, theorem 11.5 says the kernel is a subgroup and the kernel is a normal subgroup. Okay. Theorem 11.5, given any homomorphism, the kernel, so phi G1 to G2, a homomorphism, the kernel of phi is a normal subgroup. Now, when you first see this, you think, well, we should prove it contains the identity, prove it's closed under the group operation, prove it contains all the inverses. That proves it's a subgroup. And to prove it's a normal subgroup, we'll use one of the criteria for normality, that the left cosets equal the right cosets, or if you conjugate an image of the kernel, an element from the kernel via G, it's always in the kernel again. So we could go through all those steps, except we noticed that the work we did yesterday has done it all already, okay? Because the kernel is you can see from the definition, it's an example of this inverse image construction. It's the inverse image of the set containing just the identity, G2. So we can really shortcut the proof for this. So notice that the kernel of phi, it really is, it's the inverse image of this subset E of G2. Now, what do we know about the set containing just the identity G2? It is a subgroup. It's a trivial subgroup. G2 is a subgroup. But more than that, in fact, it's a normal subgroup. That's always true. The trivial subgroup is always normal in whatever group it is. Because well, it depends how you want to look at it. So, normal, i.e., for every G in G2, what happens when you conjugate an element from this subgroup by G? Well, there's only one element to choose, namely the identity. So is the identity, which again is an element of that. So when you conjugate any element to the subgroup, it is the subgroup. So that proves it's normal. So by 11.4, by proposition 11.4, kernel is a normal subgroup. Kernel of phi is a normal subgroup. Normal subgroup of G. Okay. So we don't need a whole separate proof from first principles of this. I mean, that is still instructive to go through. To go through the proof that the kernel is a subgroup and it is a normal subgroup, just from first principles, from the definition of the kernel, and using the subgroup theorem criteria for normality. Still do that. So this leads us on to our isomorphism theorems. And this first one is, well, there's a bunch of them. There's three of them. The first isomorphism theorem, the second isomorphism theorem, the third isomorphism theorem. And then in the middle of them all, there's a correspondence theorem. These theorems are all just about looking at all the different ways that homomorphisms and their kernels, how they all kind of interact, and relationships amongst them. And you see, if the kernel of homomorphism is a normal subgroup, then that means we can take a factor group, use it to form a factor group of the domain of the homomorphism. And the question is, what's the relationship of that factor group to the destination of the homomorphism? So this is theorem 11.10. First isomorphism theorem. It's got a nice picture, so we'll have a look at the picture first. Well, done. So we start off with, we've got some homomorphism represented by psi. So psi and homomorphism. Okay, we just proved the kernel of psi is a normal subgroup. So that means we can form a factor group. And what's the relationship, just kind of how can we relate this factor group to this picture? Okay? Well, there's what's called a natural homomorphism from G onto the factor group, and he's representing this with phi. So phi is the natural homomorphism from G to the factor group. Can you tell me what the definition of that is? It's natural. GH. Yeah, 5G, well, it's not called H. So it's a homomorphism from G into here.
Oh, so clarify.
Yeah, so we must send an element from G to a certain left coset. Right? Some left coset of kernel of phi, or right coset, but the left cosets are equal to the right coset, so we draw it to the left, so we just refer to left ones. So which one, but yeah, there's only one choice. It should be the left coset corresponding to G, generated by G, represented by G. Okay. That's the natural homomorphism. Let's just have a divergent. Maybe we haven't encountered that before. Yeah, because Jan was doing factor groups before the homomorphism. Okay, so let's just have a little diversion. So claim this is a homomorphism. Well, is it? Is it a homomorphism? Let's prove it. To prove it's a homomorphism, we want to consider 5G1, G2. Yeah. Well, here's the definition of phi. The definition is, and I'll put brackets just to emphasize this, it's the left coset of the kernel corresponding to that element, G1, G2. Well, how do you think about that? How did you define, what was the definition of the group operation in the factor group? How do you multiply together two left cosets? A left coset G1 times the subgroup, whatever the normal subgroup is, times G2 times the normal subgroup. How do you multiply those together? But by definition, it's the coset generated by the product of the representatives. Okay. So from the work you did with factor groups, this is equal to this product of. Remember, these are products of subsets. I mean, this is a certain subset of G. It's a coset of the kernel, coset of this subgroup of G, and it's equal to the product of these two. Okay, that was done in the. So this is from the definition of factor groups. But that is exactly 5G1 times 5G2. So just from the definition of the operation in the factor group, you see that this map, sending an element to the coset represented by it, it does satisfy the homomorphism. So what's missing from our picture is an arrow going this way, right? And this is what the isomorphism theorem is actually saying. It's saying there exists a natural, obvious map going this way. He's representing it by eta. Now, the theorem says, well, in the theorem we discover a couple of things. It's a very natural operation here. It commutes with these other two. So the theorem is saying, so the theorem says, there exists a nice map eta, well, stronger than that, an isomorphism between these groups, satisfying that psi is equal to the composition eta after phi. So that to start in G and go to here is the same as going here first and then there. Okay. And there is only one such map. So there exists a nice map eta such that eta commutes, or eta such that, so this is referred to as saying that the diagram commutes, that any route through the diagram is the same. From if you start at one point and end at another, if you follow different paths, it's the same. That's what we say a diagram commutes. And eta is the only such map, is the only such map, satisfying this problem. So the proof is to start off with the definition of eta. Now, we're defining it on the factor group, so it has to operate on, sorry, equals. You're defining it on the factor group, so you have to say what value it takes on a coset. But there's only one possible answer. Read it in the book. Yeah. See, what have we declared is going to be true of this eta? It's going to map from here to here, but it's supposed to do it in such a way that if you start in G and come this way, you get the same value in H as if you just hopped over here. So what must that value be? So you start from a little g here. Well, if we just pop over here, where do we end up? We end up at psi of g, psi of little g. Yeah, because that's what you get to if you follow this path. If you follow this path, you start a little g, you first arrive at the coset, g times the kernel. So for the definition of this map eta, we want to end it up in the same place. So we must send this left coset to psi of this representative. Yeah. It must somehow be manufactured, the value for eta must somehow be manufactured from this element of g. So it's the representative we've signified here for the coset. So this coset is represented by this element of g. So it must be something to do with g here. We want to end up in H. The only way we've got to specify elements in H at the moment is to specify them as values of the map psi. So this is defined to be psi of little g. Okay. So that's how we set out to define this map. Whoa. What's the potential problem?
then it's not commutative? Or that it doesn't exist?
Maybe that the map doesn't exist.
Because if we've gone from G to GK
Yeah.
through phi, who's to say that from GK to H that it exists? Because those could be two completely different mappings under the operation phi and psi.
Well, you see, we're assuming that psi exists.
Yeah.
This map phi, so therefore its kernel exists.
Mm-hmm.
Therefore, this map exists because this map is natural. Then it just uses psi, concept of psi. So these two exist already.
Right.
So we're manufacturing this one now out of the information that we've got. But there's another subtle kind of
Well, it's
check.
almost as if you're doing both operations in one.
Yeah. But
In such a way.
See, the problem is we're defining an operation on a coset by making use of one of the representatives of that coset, right? Remember, this object here is a coset in G, so it's a subset of elements of G. One of them is the element little g, because G times the identity, which is in the kernel, is in the subset. And so we're telling the reader how to define eta of this coset by making use of the representative little g. The reason for is that there could be other, who's to say if you use a different representative from the same coset, then maybe that potentially give you a different value over here. So the caution here is this definition well defined? Is it valid? Because if I could represent the same coset with an alternative element, and I got a different value over here, then this wouldn't be a good definition, because it would depend on which representative of this single coset you use to do the calculation. Yeah. And if this is to be a definition, it must be unambiguous what the value in H is. So the question is this definition for eta well defined? In other words, if G1 times the kernel equals G2 times the kernel. So now we introduce two different representatives for the same coset, G1 and G2. Is eta of G1 equal to eta of G2? It has to be, in order for the definition to be good, it has to be. It has to make no difference what representative you choose to perform the calculation. Because we want it to be defined. If we were just defining another map from G, that'd be okay. If we take different elements of G, it can take different values. But we're defining a map on the factor group. The factor group is the set of cosets. So the value that the map eta takes, it mustn't, if we take different representatives of the same coset, it must give the same value. Okay. So let's prove that, or answer that question. So suppose G1 times the kernel of psi equals G2 times the kernel of psi. So our destination is that eta of G1 equals eta of G2. Well, what can we do here? A consequence of that. If we've got two elements representing the same coset, one of them, G1, must be G2 times a k for some k in the kernel. Yeah? Because we're assuming these two cosets are equal. G1 is one of the elements from here. So it must be present in this coset. So it must take the form of G2 times a little k for some little k. Does that make sense? Yeah? So now we got a good relationship between G1 and G2 on the element level. So I can try applying, well, let's discover what eta of G. Eta of G1. Eta of G1 is by this supposed definition, it's psi of G1. And let me do a sneaky trick. Yes, it's equal to psi of G1 times the identity. And why have I introduced the identity?
So you can put that.
To what?
Because it's in the kernel.
Well, back to what specifically?
Kernel.
Something in the kernel? Which something in the kernel?
Two.
Which something in the kernel have we gone to the bother of naming on the page?
Ah, okay.
To K, to that particular K. So psi of K, I can represent the identity element in G2 by psi of K. What is psi? Psi is a homomorphism. It satisfies the homomorphism property. Here's a product of two values of psi, so
It's psi of G from K.
exactly. Otherwise known as G2, otherwise known as all of this.
What's the N thing?
Eta.
Eta
Correct.
G2.
Eta G2. Like the N thing, it's like an N with a downward kind of tail.
I've seen them, I just never knew
Yeah.
what they were called.
Yeah, I discovered it relatively late in life.
How do you pronounce the one that's spelled XI?
Well,
Chi.
chi test music.
Chi test. No, that's chi squared. The one you're talking about is
The DX that looks like that.
The curly E thing.
it's written as xi.
Oh, that one, yeah. Yeah.
Xi.
I'm not
It's
100%
XI
sure.
on Word, but I don't know how to pronounce it. It's just.
Yeah, maybe like a psi.
Psi is how I can do it.
Xi.
Lena pronounced it with
She
always
says-
like,
yeah,
it says
Lena says
oxide. It's
oxide.
very
Oxy,
strict.
yeah, well, I think to do it properly, you have to be Greek, or you have to
Yeah.
sound it like it.
For ages, I was typing it in on later because very epsilon. And
Very
backslash VAREP.
It's very
SILON. Yeah.
It's not epsilon, but it's very epsilon. And as soon as she said it, and I was like, I have no idea what she said. I just googled it quickly and saved it so I knew what she was saying.
Oh, I knew which one you meant though. I definitely knew which one you meant. It's like it's just spelled XI. That's it.
But it's also written some places as KSI.
KSI. Yeah.
So it's Xi.
Okay.
Anyway.
Anyway,
Carry on.
so-
Carrying on, so this answers that cautious note. It is well defined. Yeah. This definition is okay. Because if we took two representatives of the same coset, it's okay, it does come out as the same value. It is the same value, okay? Psi of G1 is psi of G2. G1 and G2 are different, probably, because G1 is the product of G2 and K. So probably G1 and G2 are different, unless we happen to have chosen to put them to be the same. But morally they're different, but their psi values are the same, because they're related by a product with an element in the kernel. And that disappears when you apply psi to it. Yeah? So psi is well defined. So that's okay. And you can obviously see now that the image or the range of psi, by definition, the range or image of psi image of eta is what? Well, it's the image of psi. Because like, what possible values do you reach after applying the map eta? Well, you reach whatever you can reach after applying the map psi. Good. So what do we have to prove? We have to prove, what did we claim? We claimed a few things. It's gone off the page. Where is it? Theorem says, there exists this nice map eta. Okay, we've done that. Okay, we have to show it's an isomorphism and show that it commutes. Well, the fact that it commutes, I think, is clear already. So by construction of eta, we have that eta after phi equals psi. Okay? Because if you start off with a g, start off with a little g up here, apply psi to it, you get psi g. Apply phi to it, you get the coset g kernel. But then apply eta, you get psi g. So you do end up in the same destination. It's constructed in such a way that you do end up in the same destination.
You're doing the operations in reverse up, and you're doing eta and phi.
After
Yeah, and you do it.
phi.
Yeah.
So phi comes first, then eta. Yeah, because they have to, because that's the way they join up.
Yeah.
But remember, like, these are maps. So when you write maps like this,
Yeah.
what's the operation?
In this case, phi after eta.
Yeah, no, but what's the
Oh,
group of operation that's joining these
Composition.
composition of functions? Yeah. Unless like it's some other weird situation, if you're multiplying together functions like that, it's composition, doing one after the other. Quite literally, applying phi first, then applying
Then
eta
doing that,
on the result of phi.
So what was that composition of group?
Composition of maps of functions. Yeah.
That was the
Yeah, sorry. Yeah. So the only remaining thing we have to show is that it is an isomorphism. Well, that it's a homomorphism and that it's an isomorphism. So we show that it has the so now we show eta is a homomorphism. It's by definition it's surjective onto the image of it surjects onto the image of psi. So we'll show it's a homomorphism and we'll show it's one-to-one. So to show eta is a homomorphism, you have to think about applying it to the product of two cosets. If I call them G1 and G2, but we've just been using G1 and G2 to represent the same coset, but now I want to talk about two different cosets. So in fact, I'll use a G, well, he uses G1, G2, but let's use a G prime. So two different cosets. Right. Well, what is the meaning of the product of these two cosets? Its meaning is the coset represented by GG prime. And we apply eta to that, we apply that by psi of GG prime. Right, that's the definition of eta. Eta is a homomorphism, so this is e to g. Sorry, psi is a homomorphism, so this is psi of g prime. Well, what's that? That is eta applied to g times the kernel, and this is eta applied to g prime times the kernel, just by the definition of eta. And from beginning to end there, you've got the homomorphism property for eta. Yeah. So eta eta is a homomorphism. So as we've just noted up here, a better way to write it is as it does in the book. So by construction, eta is surjective onto the image of psi applied to G. Because our mapping diagram, so this mapping diagram will work. So there's the image of G, or the image of psi over here, psi applied to G, some subset probably of H, but eta surjects onto that. Okay? Because if you want any element of the image of psi, so you want any psi of G, well, you just apply eta to that, to the coset represented by that image. So you can achieve anything in the image of, that's an element of psi of capital G. So you can achieve any element of that by applying eta to a suitable coset. So the remaining thing, because we want to demonstrate that eta is an isomorphism, so it remains to show eta is injective. Sure. 1-to-1. But we've kind of already shown that, I think, when we showed the. Oh no, we haven't. No. I was going to say we kind of already shown that when we showed the 1-to-1. Probably showed the well-defined, but not quite. So how do we show eta is injective? So we assume eta of G equals eta of G prime. Sorry, not. These are cosets. Eta of this coset equals eta of this coset.
Is that if remains or H remains?
It remains.
It remains.
It remains. So just a comment on where we're at in the group. It remains to show that eta is injective. Because we want to show that eta is an isomorphism.
Yeah.
We know it's a homomorphism.
We're trying to disprove
Well, what do we want to conclude here at the end of this argument? We want to conclude that these two cosets are the same. Yeah? And that will show that it's injective. Yeah? But if you have two cosets that gets mapped to the same value under eta, it's because they are the same coset. Not because eta is collapsing different elements down onto the one. Yeah. So, but see, this implies that psi of G is equal to psi of G prime. Well, what does that imply? It implies, for instance, well, you can take one of these over, so that psi of G times the inverse of psi G prime is the identity. Okay, two things about inverses, about homomorphisms. One, the inverse can come inside. Try to avoid this. So you know what I mean? This is the inverse of G prime, the element G prime. But psi is a homomorphism, so that implies psi of G times the inverse of G prime equals the identity. And that implies that the product of these two, whatever it is in the kernel of psi. Because it gets mapped to the identity. by definition, it's something in the kernel. And if it's something in the kernel, well, this was, if you look back at our initial kind of technical results about cosets, if an element times the inverse of another element is in the group, that means their cosets are equal. Probably in 2, 6, so it means back in, maybe this was back in the ones. Chapter 6, sorry, back in chapter 6. Lemma 6.3. Observe. Okay, lemma 6.3 said all these were equivalent. The cosets are equal is, oh, well, okay, it was organized slightly differently. But the product of one of the elements times the inverse of the other one is in the coset, is in the sort of group. That's the same as saying the cosets are equal. Yeah.
That was the conclusion we've just drawn there.
So that was lemma 6.3. So we're invoking lemma 6.3. Okay, we're taking the inverse of the second one rather than the first one, but that's just amounts to renaming them by lemma 6.3. Yeah. So from start to finish there, that proves it's injective. Because if you observe eta taking the same value on two cosets, it's because they are the same coset. So eta is injective. So that proves the theorem. Now, so in summary, if you've got any homomorphism, G to H, G to H a homomorphism, it means we can build a model of what does the image of the group G look like inside the group H? We can build a model for it out of G by taking the factor group. The factor group G mod the kernel psi. And this is what we've just proved here, is that it's isomorphic to the image of G, and that's some subgroup of some subgroup of H. So it gives us a way, if you like, to understand that what the homomorphism is doing. Okay, it's sending the group G into the group H. It's maybe collapsing elements. It's maybe losing information. There might be a lot of detail in G, but if you're sending multiple elements to the same image here, you're losing that information, if you like, because you're collapsing different things onto the same thing here. But we can understand it as a construction out of G by using this construction method that we've already looked at, which is building factor groups, which we've already studied this, and we kind of understand this as a way of simplifying the structure of the group G. Because you take all the detail there is amongst all the elements of G, but you group elements together in the cosets. And then you look at the group operation juiced on the cosets. So it's a less detailed view of G. The most detailed view you can have of G is looking at the operation on all the individual little elements of G. If you start grouping them together, just look at how those cosets operate with each other. You've lost information. A less detailed view of the group. So this first isomorphism theorem gives us a way to understand that that's what's going on when you have a homomorphism of the group. Okay? If it's not an isomorphism, remember the things we studied first were homomorphisms that were bijective. So they didn't lose any information. They didn't collapse different elements onto the same image over here. It's just a bijet, a one-to-one and onto map. And then that said that this group was isomorphic to that one. It was effectively the same, or an equivalent group. But homomorphisms, if they're not isomorphisms, they lose information about the group because they're equivalent to forming a certain factor group. So what this theorem is doing for us is it's saying, okay, we've introduced this new concept that we can map a group into another group with a homomorphism, but it's already captured by something we already understand, this factor group construction. It's not giving a whole different way of, representing the group G. It's already captured by this factor group construction that we've looked at.
At the end of the argument, to show that it was injective, how you've got G prime inverse is equal to the identity. That's like
not
information
the psi of it
Yeah.
is equal to the identity.
how that information has been sort of like almost lost.
Yeah,
Yeah, it's just,
because this in G, this is probably a non-identity element in G. But psi maps it to the identity.
yeah.
So it loses that info, this is like the null space. It collapses things onto in some areas of algebra they call that action the killing action of psi. Psi kills this element.
Right.
It sends it, the identity is the dead element. Yeah. It's an interesting way. And so it's a psi is killing this element because it's sending it to the identity. And the null space has that idea. The null space is everything that gets killed. That's just compactified to nothing. Is a group theory sense. Group theory sense is the identity element. And the identity element is nothing because when you operate on it with another element, you operate on another element with the identity element, it doesn't change it.
No.
It's the ineffective element. You're dead. You're very ineffective.
It's sort of like neutral ground between two people arguing. I'm on no one's side.
Okay. I went through that very slowly. The other theorem